All right, let's get into it. We're all pretty used to AI that gives us answers in the blink of an eye. But what if the next giant leap for AI isn't about thinking faster, but actually thinking slower? Today, we're going to break down a brand new architecture called energy-based transformers. And the whole idea behind them is to mimic a deeper, more deliberate, and frankly, more human way of solving problems.
So to really get this, we have to borrow an idea from psychology, this concept of two systems of thought. First, you've got System 1. That's your fast, automatic, gut-feeling kind of thinking. It's how you instantly recognize a friend's face or know the answer to 2 plus 2. Then there's System 2. That's your slow, deliberate, analytical brain. It's what you fire up to solve a tricky math problem or plan out a complex project. One's basically instinct, and the other is pure reasoning.
And this is the absolute heart of the problem that this research is trying to solve. For all their incredible power, today's AI models are masters of System 1. They are amazing at spotting patterns and spitting out quick, intuitive-feeling answers. But they can really struggle when you throw a problem at them that requires true System 2 skills. Deep reasoning, handling totally new situations, or thinking logically beyond what's just in their training data.
So here's how we're going to walk through it. We'll start with this whole fast versus slow thinking problem in AI. Then we'll introduce the model that's designed to think slow. After that, we'll look at the proof. Does it actually learn faster and think better? And we'll wrap it all up by talking about what this new paradigm could mean for the future of AI.
Okay, which brings us to the big question from the research paper itself. Is it actually possible to build a model that can learn this deeper System 2 style of thinking all on its own, just using unsupervised learning without needing any special rewards or human guidance? Well, it turns out the answer is a resounding yes. The secret sauce here is something called an energy-based model, or an EBM. And the core idea is actually super intuitive. It's almost always easier to verify a solution than it is to come up with one from scratch. Just think about a maze. Checking if a path works is easy, right? But finding that path in the first place can take forever. EBMs are trained to be expert verifiers. They learn to assign a single number, an energy score, to any possible answer. A low energy score means, yep, this looks great, it's a good match. A high score means, nope, this is a bad fit, try again.
So how does one of these things think? Well, instead of just blurting out an answer in one shot, it treats the whole process like an optimization problem. It literally starts with a random guess, just total noise. Then it uses the EBM to score that guess. Based on that score, it tweaks the guess, trying to find a version with a lower energy. It just keeps repeating this process, improving the answer step by step. It's kind of like a ball rolling down a hilly landscape, always searching for the absolute lowest point in the valley. That's the most stable, lowest energy solution.
And this whole iterative process, this thinking it over, gives these energy-based transformers three really unique abilities. You can think of them as the building blocks for true System 2 thinking that really sets them apart from other models out there. Now, check this out, because this table really lays it all bare. You've got your standard transformers, RNNs, even those powerful diffusion models. And look at the columns: dynamic compute, the ability to spend more brain power on hard problems; modeling uncertainty, basically knowing when it's not sure; and prediction verification, the ability to check its own work. Only the EBTs get a checkmark in all three boxes. This isn't just a small tweak, it's what makes them a fundamentally different beast.
Okay, so a fancy new architecture is one thing, but for it to be actually useful, it has to be practical. It's got to learn from data efficiently. So let's shift gears and look at the hard evidence. How do these ZBTs actually stack up during that all-important pre-training phase?
I mean, this is really the multi-billion-dollar question in AI right now, isn't it? Can this cool new approach actually learn more efficiently than the good old transformer architecture that powers basically everything we use today?
And this chart just says it all. What you're looking at is the scaling rate. It's just a measure of how much smarter a model gets as you feed it more data or give it more parameters to work with. And on every single axis the researchers looked at, the EBTs just clearly and consistently outscale the standard Transformer++ model. It's not even close.
The key takeaway number is this: EBTs can achieve up to a 35% higher scaling rate. So what does that really mean? It means they're way more data efficient. They squeeze more learning out of the exact same amount of information. And as high-quality training data becomes the biggest bottleneck in AI, that kind of efficiency is, well, it's an absolute game changer.
So we've established they learn faster, which is huge. But can they use that knowledge to actually think better?
Does this unique architecture translate into better performance when it's faced with a genuinely difficult problem? Let's see if they're not just faster learners, but smarter thinkers.
You know, this quote from the paper really hits the nail on the head. An AI that's always 100% confident, even when it's wrong, is frankly dangerous. Real intelligence means knowing what you don't know, and that energy score in EBTs gives them a natural way to show uncertainty. A high-energy, bumpy landscape means, I'm not so sure about this, while a smooth, low valley means, yeah, I'm pretty confident in this answer.
And this is where that System 2 superpower really comes into play. This chart shows what happens when you give a model more time to think at inference. The standard transformer, it barely improves. It gets one shot to get it right, and that's it. But the EBT, its performance gets way, way better, especially on these tough out-of-distribution problems, things it has never seen before.
Let's put a hard number on that. When you give them that extra thinking time, EBTs improve their performance by 29% more than the standard transformer. This is direct, measurable proof that their ability to chew on a problem and refine an answer, to think slow, actually leads to better results on the kinds of hard problems we really care about.
And hey, this isn't just about text. For images, EBTs actually beat the super powerful diffusion transformers at denoising, and they do it using 99% less computation. And just like with language, they get much better when faced with new, out-of-distribution data, which strongly suggests they're better at generalizing what they've learned.
Okay, so we've seen the evidence. EBTs learn faster and they think better. But the real implications here go way beyond just building a slightly better model. This could actually be a fundamental shift in how we think about building intelligent machines.
What this all boils down to is a move away from what the paper calls amortized generation, which is a fancy way of saying the model just spits out a pre-calculated answer, and a move towards iterative reasoning. So instead of just matching a pattern, the model is actively problem-solving. It's a leap from being a brilliant but brittle memorizer to being a more robust, deliberate reasoner that actually checks its own work.
And that really leaves us with this final thought to chew on. For years, the race has been all about making AI faster. This research suggests maybe we should have been teaching it to be slower, more thoughtful. If we can actually give AI a true System 2, the ability to really reason through new and complex challenges, what kinds of huge, long-standing problems in science or medicine or engineering might we finally be able to solve?